The first swap algorithm implemented in MCUboot is what we refer to as swap scratch. For this algorithm, we need to have two slots, a primary slot, shown here with a yellow image in it, and an upgrade slot, shown here in blue. In addition, this algorithm requires an area known as scratch that will be used to hold parts of the images as they are exchanged. This is shown by the small gray area at the bottom. This algorithm divides the images into segments that are the same size as the scratch area. This will need to be a multiple of the device's underlying erase size. Making scratch larger than a single erase unit can help mitigate some of the uneven wear that this algorithm causes to the scratch area. We will see shortly why this algorithm causes this uneven wear, and we will see with the newer swap algorithm how we can improve this. For our illustrated example, the image slots are 4 times the size of the scratch area. MCUboot is able to handle the case where the images are not an even multiple of the scratch size, in which case the last segment will be smaller than the others. In order to keep this illustration a little bit clearer, I'm not showing how MCUboot records the progress of this algorithm. There are several ways this can be done, with the primary implementation being to store the state at the end of the last segment. There are details as to how it finds the current version, as the data is moved around, and that is best explained in the design document. Keep in mind that every time something is copied to a new location in Flash, this state information is also updated, so that in the case of power loss, MCUboot will be able to continue the swap operation from where it left off. The algorithm begins by moving the last segment of the second slot, the upgrade slot, the blue segment 4 in our example, into the scratch area. It is then able to move the last segment of the primary slot, yellow segment 4, into this newly freed space. Lastly, it will then copy the data from the last upgrade segment, blue segment 4, into the primary slot, segment 4. This completes the swap of the last segment of the two images. At this point, these pieces of each image have been exchanged. We simply need to repeat these 3 steps for each of the remaining segments. In our case, we will exchange segment 3, then segment 2, and finally, segment 1. Once all of the steps have been completed, MCUboot will then update the trailer, not shown, to indicate that the copy has finished. The swap of each segment requires 3 erase and write operations, 1 for the segment of each slot and 1 for the scratch area. Since the same scratch area is used for each segment, it will be erased and written as many times as there are segments. In this case, there will be 4 erases of scratch each time a swap is done. Because erase cycles are the primary limiting factor in most Flash device lifetimes, this means that it is likely that the scratch area will be the first area in Flash to wear out. In realistic devices, the erase size can be significantly smaller than the size of the images, which means that the scratch area will wear at quite a bit higher of a rate than the rest. Whether or not this is an issue depends on how many times the device is expected to be upgraded. One way to mitigate this, somewhat, is to make the scratch area larger. For example, doubling it can reduce, by half, the number of erases that need to be done. However, this means that more of the Flash is needed for this scratch area, taking away space that could be used for code. Because of this, MCUboot has also implemented a new scratch algorithm known as swap move that we will look at next.